Hi, I am Sanjay Patel. In the last lectures, we have proved working rules of limit of function. Just in this lecture, I want to make a note about these working rules that one should keep in mind that these conditions, the working rule conditions, are only sufficient but not necessary. Meaning is, say for example, if we have limit x tends to a, f of x is equal to L exists, and limit x tends to a, g of x is equal to m also exists, then that implies we can write limit x tends to a, fx plus gx is equal to L upon L plus m. We have proved this thing. Okay, so this condition is only sufficient but not necessary. For the limit of fx plus gx to be L plus m, these two things are sufficient. Means we can have limit of fx plus gx equals to m, fx plus gx equal to L plus m, but this is not true. Maybe limit of fx is not L, or limit of gx is not m, or both may not exist. So to understand this more clearly, that why these conditions, why the rules, working rules conditions are only necessary, working rule conditions are only sufficient but not necessary. So I have to take one example for that. But before I explain that example, let us make it more clear by using this particular example. So first I want to prove that limit of a particular function does not exist. So let me consider this function f from R to R be defined as say fx is equal to 1 if x is a rational number, means if x belongs to Q, is equal to minus 1 if x is not a rational number, means x is irrational number. Okay, so consider this function. So function takes the value 1 when x is rational, and it takes the value minus 1 when x is irrational number. So this example is a very useful one, and very important to discuss the counter examples for this converse is not true. Like one of the thing is limit x tends to fx plus gx is equal to L plus m, but we can have limit of fx and limit of gx does not exist. So I will make use of this this example. So first let me prove this separately. Thing is, prove that limit x tends to a, f of x does not exist. Does not exist, and this is for every a belongs to R. Whatever the real number is given, the limit of this function is does not exist at any point a. Let us prove this. So I'll prove this by contradiction. Suppose if possible this limit exists. So suppose if possible limit x tends to a, f of x is equal to L exists. Okay. then we know for every epsilon there is some delta such that that epsilon delta condition is satisfied. So in particular, for epsilon is equal to 1 greater than 0, we can find some delta such that whenever 0 less than mod of x minus a less than delta implies mod of fx minus L is less than epsilon, which is equal to 1. Okay, remember here that this number a is any real number. Okay, I am not putting any restriction on this a. Here a is any real number. I must write in the beginning that a is arbitrary. So let a belongs to Rb anything. And now we are assuming that limit of function fx at the point a is L, and then we are writing this. What is the meaning of this? This implies L minus 1 less than fx is less than L plus 1. Okay, and this I can write as x belongs to a minus delta comma a plus delta minus singleton a, because this is the deleted neighborhood of the point a. So we have got this thing. Okay, now every interval contains infinitely many rational numbers as well as irrational numbers. Okay, every interval contains infinitely many rationals as well as irrationals. So if this x which we are taking, because this condition is true for all x in this interval, so if x is rational, if x belongs to a minus delta comma a plus delta minus a, and x is rational number, x is rational number, that is, I can say x belongs to Q, then in this case we have L minus 1 less than 1 less than L plus 1, because by our definition of the function fx is equal to 1 if x is rational and is equal to minus 1 if it is irrational. So this gives me this 0, this 1 will be, if I consider this first, so 0 less than 1 L, and if I consider this, what I will get is it is less than L minus 1. If you take this 1 on this side, it is less than 2, correct? First consider this inequality and then consider, say, this inequality. Remember, everything is true. L minus 1 less than 1 gives you L less than 2, and 1 less than plus 1 gives you 0 less than L. So finally I get this thing, 0 less than L less than 2. Now consider another possibility, because here x is any real number in this interval, so it can be irrational also. So second possibility, if x belongs to a minus delta comma a plus delta minus singleton a, and x is an irrational number, x is an irrational number, then we have from this star L minus 1 less than minus 1 less than L plus 1 because of star. Okay, here also we are using the star. So this gives us, if I take this one, L minus 1 less than minus 1, I will get L is less than 0, and this gives me, if I consider this part, let me write this way, if I consider this first, it gives me minus 2 less than L, so I am writing here minus 2 less than L, and if I consider this part now, it will give me L less than 0. Okay. So this is our result number 2. So what we have proved actually? In 1 we are saying that 0 less than L less than 2. Okay. In 2 we have proved that L is between minus 2 and 0. But what is L? L is a limit of the function. So limit is always unique, and we cannot have two different values of L. One is between 0 and 2 and other is between minus 2 and 0. So since limit of the function x tends to fx is equal to L if it exists is unique, 1 and 2 gives the contradiction. Is they exist, we cannot have 1 and 2. Okay, so we are getting a contradiction. So this is something wrong. So our supposition therefore must be wrong. What is our supposition? Our supposition was this limit x tends to fx equal to L exists. So this is wrong. So what is proved? Limit does not exist. So I can say conclusion. So thus limit x tends to a f of x does not exist. So very important example. Remember, if a function fx defined as 1 as x if x is rational and minus 1 if x is irrational, then its limit does not exist for whatever a we choose. Okay. Now using this example, we can discuss that the conditions in the working rules are say only sufficient but not necessary. So consider this remark, or let me write this way. Instead of remark, let us make it a nice question like this way. Another example, very interesting one. Give an example to show that limit x tends to a fx plus g of x exists, but neither limit x tends to a fx nor limit x tends to a g of x exist. Okay, so very interesting one. In short, we have to show that we can have limit of fx plus gx exist, but neither limit fx nor limit gx exist. And this can be explained using our previous example with some modification intelligently. So I am defining two functions f and g using the previous example like this. Define f from R to R as fx is equal to the same thing 1 and minus 1. Please understand, if x belongs to Q and if x is not in Q, means if x is irrational. And now the important step, define a function g from R to R as g of x is equal to, see the change, I am defining g of x as minus 1 if x belongs to Q and is equal to plus 1 if x does not belong to Q. Just it is reversed. Okay. So what will happen? Remember, function f and g both are defined on the same domain, so the sum is possible. and the sum is given by, okay, we have fx plus gx, or the function f plus g from R to R is defined as, this function is defined as f plus g of x, okay, which is equal to fx plus g of x. Let me write this way: f plus g of x is equal to this for every x belongs to R. For every x belongs to R. This is equal to, here x is in real number, so it can be rational or irrational. So if x is a rational number, if x belongs to Q, then fx is plus 1 and gx is minus 1, correct? And if x is irrational number, then fx is minus 1 and gx is plus 1. Fx is minus 1 and gx is plus 1 if x does not belong to Q. So what is your conclusion? Clear? In any case, whether x is rational or irrational, the sum of fx and gx is going to be 0. Note that this thing is 0, okay, and this thing is also 0. So thus, in any case, f plus g of x is equal to 0 for every x belongs to R. So it is a constant function, and therefore limit of f plus g of x at any point is nothing but limit of the 0 function, which is a constant function, and therefore its limit is 0. So this limit exists. But as I have discussed in the previous example, that limit of fx does not exist, and the same reason, just it's interchange of the values. So limit of fx and limit of gx does not exist. It follows from the previous problem. So I can say this limit exists, but okay, this exists, but limit x tends to a fx and limit x tends to a gx both do not exist. Both the limit do not exist. So the converse of that result or working rule is not true, or the conditions in the working rule are not say necessary. They are only sufficient condition. Another, the same example you can use to show the converse is not true in case of that last working rule, which is the modulus function. So I can say, show by an example that say mod of fx tends to mod L, but fx does not tend to L. But fx does not tend to L, or even if fx may not exist. So converse of that working rule is also not true. The same example will work, because for the same example means if I consider fx to be the same function, if we consider fx is equal to 1 if x is rational and minus 1 if x is irrational. So just let me write systematically that f from R to R be defined as fx is equal to 1 and minus 1 according to as x is rational or x is irrational, means x is not in Q. Then it is clear that the mod function mod f from R to R, which is defined as mod fx is equal to mod of f of x for every x that gives us always 1 whether x is rational or irrational, because if x is rational it is mod of 1, and if x is irrational it is minus 1. So minus 1 will also give us plus 1. So this is true for every x belongs to R. And as a result of this, mod f is a constant function in this example. So limit of this constant function exists. Okay, this limit exists for any point. So limit x tends to a, whatever a is, mod f of x, which is nothing but limit x tends to a of 1 is equal to 1. So this limit exists. Okay, but we know that limit of fx does not exist. But limit x tends to a, fx does not exist. Okay, so these are the discussion about the conditions of working rules are only sufficient but not necessary. Okay, and in the next lecture we will be proving 2 important results, namely the sandwich theorem for limit of functions, and also the relationship between the limit of sequence and limit of function. Okay, thank you.